right, j cap, whatever. Now to make this system move, I had applied a horizontal force f of t as I had defined in the problem at the very beginning to be equal to some initial f0 times cosine omega t, if you remember, cosine of omega t, and this is the external non-conservative force acting on the system to make it move. This is the total force acting, the net force. Now we can break it up into components, like one will be along the rod and the other will be in a direction to satisfy the triangle law of vectors, basically like this. Now if this is theta, this is theta from geometry. What is this? This is basically f of t. I'm not writing f of t as that full expression, I'll substitute it at the end. So f of t of sine theta, and what's the direction of this axis? It's I direction, I cap. What is this component? F of t cosine theta, and this direction is j cap. So basically j direction, j cap. Now what is our virtual work done? The net force is computed in terms of unit vectors. What is our virtual work done? Like it is denoted like this, the virtual work done. That is the force along the x1 direction dotted with our displacement, which will be a function of x, and there is only one x here, so only one del x1, and this is turning out to be equal to the total force f of t dotted with, is it visible? No. Let me rub the board. So basically the virtual work done, that small virtual work done along that direction of the del x1, it is equal to that force, non-conservative. The virtual work is non-conservative in nature. So the force dotted with our dr. What is the dr? This is the dr. And what is this equal to? Now for qx1, I write f0 cos omega t. This is f of t, and the directions associated with it to make it a vector, sin theta I cap plus cos theta j cap, yeah. And that this whole expression is of force vector dotted with our del x1, basically del x1, and x1 is in I direction. Now what is the dot product? x1, so I dot I is the same expression, you just get the multiplication, I dot j is 0. So what you get is that we get the qx1 dot del x1 is equal to f0 cos omega t sine theta del x1, right? This is the thing, you cancel the del x1s, you basically get your RHS as equal to q x1 is equal to f0, this term times sine of theta. This is your RHS. The force which is acting along x1 direction is this force with this, which is going with this work done, virtual work done, and so we get the final equation of motion along x1. We are left with another case, so but our first equation, this should be the force equation, turns out to be along x1 direction m2 x1 double dot, if you remember the LHS, something like this. This is equal to f0 cos omega t sine theta. This big an equation, but it has got some great importance. This is the equation which we get for the motion along x1. Now that means not along x1, like motion equation for x1 as a coordinate. Now that means this should be a force equation, perfectly force equation. See, this is m times acceleration force, this is centripetal force m omega square r, this is a kind of expression which is the spring force, the spring constant multiplied with the amount by which the spring stretches. So this is spring force, and basically this is our force due to gravity, and this is our non-conservative force. And to do a check if this equation is correct, you can do a static check. This equation, if it is correct, it should pass the law of static equilibrium. That is, if you make every x1 0, the whole thing should turn out to be something so that our motion is at rest, our system is at rest. So if you do that, well, yeah, it passes the law of statics. Make this 0, these two terms become 0, this becomes some constant, and this is a constant, and this is a constant. So you're left with the constants that is with as per the law of statics. And so we proceed to the next part. So now in this problem we have to find the swinging motions equations. That is, it's in the j direction. Now why in the j direction? Because again, if you refer to the diagram, it is evident that the thing was oscillating like this, right? So what's the direction in which it is oscillating through theta? That direction is this j direction. So that is why we are left with finding all the 1, 2, 3's with respect to theta. Now we will do our partial derivatives of kinetic and potential energies with respect to theta, because we have two generalized coordinates. One is this x1 and the other is this theta. So we go through Lagrange twice to completely describe the system, and this new set of equations which we will get should be some kind of torque equations, and for that I'm doing it in black. So basically the first term which you will get, basically I'm trying to say that if you do this d by dt of partial of t with respect to partial of theta dot, okay, you can do this. I'm writing the end result because it will take some more time. It's basically I zz1 times g I zz2 g2 I zz2 plus some term x2 m2 x1 whole squared, and that times and this times our theta double dot and some additional terms, yeah, they're visible, to m2 x1 dot theta dot. Basically you can do this expression, you can compute this partial derivative, and then I'm just directly writing what I will get if I compute this one. If you compute the partial of t with respect to theta dot, you get this expression, then dy dt, that makes some double dots appearing here and there, and this is the net expression which I'm getting, this piece. Now observe here that what is this? Moment of inertia of the rod about zz1 axis with respect to the point A. What is this expression? Moment of inertia of the rod, of the sleeve about that point A. Basically this whole expression means AIZZ2. Moment of inertia of the sleeve along ZZ2 axis about that point of suspension A. Why? Because you see, this is something similar to parallel axis theorem. Basically that A and the center of mass axis were like this parallel, the distance between them is x1 squared and times m2 plus the moment of inertia about its center of mass. So this composition is basically, this is what we are getting, but we are keeping it like this. I just wanted to point out that this is moment of inertia of the rod about A, this is the moment of inertia of the rod of the sleeve about the center of mass, and this when added to this makes it something similar to what you will get from parallel axis theorem. Like I'm saying that this is one axis of rotation and this is point A, and this is for the sleeve, this is one axis of rotation along its center of mass. Basically this distance is what I chose as x1 to simplify things here, as you see. So this x1 times m2 squared, so m2 times x1 squared plus the moment of inertia of this sleeve along its axis of center of mass. So basically that gives us the moment of inertia of this sleeve with respect to this point. That is what I mean to say. So we are going correct so far. What is our second term? Let us find the second term. This was the first term. The second term is nothing else but minus this term. right? Now t with respect to theta, it turns out to be 0. There is no single term because t is simply not a function of theta. So how will you do the partial? It's constant with respect to theta. So this is 0. Now what is the third term? It is plus partial v with respect to partial theta, and that we are what we are getting. I'm writing the final result again. It is basically m2g x1 sine theta plus m1g L1 by 2 sine theta. This is the net expression, the third one. Yeah, it's visible. And this is basically this quantity. And so we rub this up. We have found out our LHS. I'm not summing it up. I will do it at the end. Now the most important part, we are left with our RHS. What's the RHS? The fourth part, we have to find this q theta. Now remember, in the previous example, in the previous part, for the x equations, the force equations, we wrote qx. This is the torque for theta, or the force producing the torque for that motion along theta. Now basically, this when dotted with your dr will give you your virtual work done, non-conservative, for the coordinate theta, along the coordinate theta. The rotational work done due to the torques acting. Now I know the force, it is F of t times its components, if you remember, sine theta I cap plus cos theta j cap. This is the force dotted with dr, right? What is dr? Well, if this is the diagram, this is the rod, this is the sleeve, and this thing is moving with respect to theta. It is oscillating like this. The rod is moving like this, swinging, and in the swinging motion, dr is basically that small arc length, like this small arc length. This one is dr, and what's that? It's this length, that is x1 plus L2 by 2. Like x1 is this much from point of suspension, and this length is L2 by 2. So basically x1 plus L2 by 2 times some small angle. This is some small del theta. This is some small angular displacement del theta. And this is the arc length. The momentum is x1 plus L2 by 2, the arc length. So basically this is the arc length dr. So this is dr, which is a function of del theta, and we have this additional term to account for, this geometry, this, the arc length in terms of radius and angle. So we have got our dr as this expression, and basically we can find our force from here. The force along this direction of dr, we have to find the force along the direction of this dr, which we have found. Now we are computing that single piece of computation. Angular virtual work done is this thing, cos theta, the dr. So basically the dr is in the g direction, the z direction, j cap. Now this becomes 0, so I get the cos theta, and now I have that extra term which was there for dr, and I have my del theta. You simply know that this is equal to q theta times, so cancel them. So what is our q theta? It is basically, q theta is basically f0 cos omega t cos theta times x1 plus L2 by 2, right? It's visible. This is our RHS, force acting along the theta, and the momentum. This is the force we are getting along the dr, which will account for the virtual work done, the small virtual work done. And so you just equate one and the LHS and RHS, and the final equation of motion is achieved. And you see, this is a torque equation. This is a torque equation. Tau equal to I alpha. If you remember, we got the torque equation. I'm writing it. Basically, the torque equation then becomes, if you add those terms, actually, you got some I terms over here, some I terms with some theta double dot squared. So this means I alpha, double dot means alpha, I alpha square. And so basically, no, sorry, I alpha was there. Yeah. So I alpha, so torque is equal to I moment of inertia times the angular acceleration. And basically this is what you got in the LHS with some additional terms. Those were also torques, and the force equation we got, that is also a torque, because that is force times distance, so that is torque couple. And so our second equation for theta is basically what you get by equating those two pieces. And thereby I conclude this problem session. Happy problem session. Enjoy physics.